Section 16.6 is about surface integral. These are brand new type of integrals. We have never seen these before, so hopefully you will understand what exactly surface integral is and what will be its application in real life. This is section 16.6 in Thomas's textbook, which is the same as 16.7 in Stewart's textbook. When we say surface integral, just like line integrals, which the value of the line integral depended on the path or the curve, as you can tell by the title of this section, the surface integrals are type of integrals whose value depends on the surface. So depending on which surface you are, you get a brand new value for the integral. Not to be confused with the surface area. These guys do not, I repeat, do not compute surface area unless the integrand, which we will see momentarily, is equal to 1. So somehow they are related, but it's not about surface area. Yes? In other words, it doesn't compute surface area. So what we have to do is, suppose we have a parametric surfaces. Suppose that S is a surface with parametric equations of x is equal to, let's say, some function of u and v. Y is equal to some other function of u and v, and z is equal to some other function of u and v. So these are parametric equations of the what? Of the surface, correct? Now, the definition of surface, the definition of the surface integral goes as follows. Surface area of, let's say, fxyz over the surface S is defined as double sum, evaluating the function at some sample point on the surface, times the area of little piece of the surface area, which we call it the patch. So this would be a patch on the surface area. In other words, to find the surface area, I peel off a little skin of the solid, find its what? Area, and lo and behold, what? Multiply that little area of the little piece of patch by the value of that, what? Let's say the function at specific point on that patch. And I repeat this infinite many times. Lo and behold, that would give me the value of the surface integral. Just like line integrals, surface integrals can be evaluated over a scalar function like this. Also, they can be evaluated over vector field, which is in part 2 of this video. And those are called flux integrals, and we will see what the application of those guys are. For now, we'll be concentrating on surface integral over so-called scalar functions, correct? Scalar functions. So these are not vector field, they are good old function which we have been dealing with since the beginning of the semester, correct? So if you remember way back in chapter 12, the area of a parallelogram determined by these two adjacent vectors is magnitude of what? A cross B. So what happens is if you pretend this little patch is approximately the same as what? A parallelogram whose sides happens to be, let's say I draw these tangent lines at this point, okay, and then that tangent line, and let's say this guy is partial of r with respect to u du, and this is like partial of r with respect to v delta v. That's delta u delta v. So if I pretend this little patch is like a what? Is like a parallelogram. So therefore, the area of this little patch can be approximated by the area of this parallelogram whose adjacent vectors or sides happens to be partial of r with respect to u delta u and partial of r with respect to v delta v. So if I take the magnitude of that, so magnitude of these two, the cross product of these two vectors and then their magnitudes, that would give me the delta S, which is the surface area element of that little patch. So what we get is ultimately is the following formula for computational purposes. So to find or evaluate a surface integral over a scalar function, all you have to do is what? Express the function in terms of parametric equations of the surface, multiplied by magnitude of what? Partial derivative of the vector not form of the surface with respect to u, and cross producted with partial derivative of r with respect to v dA, and then this would be over region r. Depending on what dA is, that determines what r is. In other words, if dA is dy dx, then this would be like what? XY plane, and so on and so forth. Special case, if z is explicitly in terms expressed in terms of what? Function of x and y, then this formula changes into what? F of x, y, x comma y comma g x y times, so this magnitude of the cross product changes into square root of 1 plus dz dx squared plus dz dy squared dA. So this is a special case of this guy when the function, the surface is a function which can be explicitly expressed in terms of x and y. Otherwise, if the function is given to parametrically, it is, you know, it would be advised that what you use this formula over this. This is only used if z can be expressed as explicitly in terms of what? Function of x and y. So there is a similarity between surface integral and line integral. If you remember, line integral was over arc length, whereas this guy is over area element. And remember up there, we expressed the function in terms of parametric equation of the curve and multiply it by magnitude of r prime, which was the same as if this r prime was velocity, this was speed dt, where t goes from what? A to b. It's kind of like the same analogy, except this magnitude of r prime replaces with magnitude of what? Partial of r with respect to u, cross partial of r with respect to v, and the dt gets to be replaced with dA, and still the function gets to be evaluated in what? In terms of parametric equation of the surface, as opposed to parametric equation of the curve for line integral. So the relationship between the surface integral and surface area, it is pretty much the same as relationship between line integral and arc length. In other words, arc length was a special case of line integral. So surface area is a special case of surface integral. Then again, here it is. Here's a special case. Suppose in your what? Surface integral, the integrand, the function fxyz is equal to 1, identically equal to 1. Then in that case, this double integral, which denoted by, double integral with what? Um, Subscript of s, which stands for what? Surface integral, does compute the surface area of the surface S. So that's a special case. In other words, surface integral is a general case of this special case in which the integrand happens to be 1. If the integrand is 1, so what you're finding is the surface area of S. Otherwise, you are not finding the surface area. It's just a title, which means the value of the integral depends on the surface. Just like when the integrand was 1 in line integral, that was a special case because the integral, the line integral, will compute the arc length of the curve. Here, if the integrand is 1, the surface integral is computing what? The surface area of the surface S. So, as I said, just like line integral, if the function was 1, you were computing the arc length of C. So with that said, let's evaluate this surface integral. So this is your function of what? fxyz, which happens to be y in this case. And ds, this is like what? This is like area element. Okay, this is like area element. And now S is the surface, Z is equal to x plus y squared. That's like cylindrical surface. X goes between 0 and 1, y goes between 0 and 2. So what you do, because this is one of those special cases, you have a z's function of x and y. There it is. So we use this magic formula right there. So, this guy, square root of 1 plus what? Partial z with respect to x squared plus partial z with respect to y squared is what? Equivalent to what? If you would have what? Express, or I should say, express the equation of the surface in parametric form. In other words, this would be the same as partial of r with respect to x, what? Partial of r with respect to y magnitude. So this guy replaces this guy. However, if you decide to go by that formula, then notice the vector equation of your what? Surface is x comma y comma x plus y squared, because z was x plus y squared. And remember, to parameterize the surface, I always need two parameters. So when you set this up, you get this kind of integrand, which is 2 plus 4y squared. But if you let what? This entire radicand to be u, which is 2 plus 4y squared, du is almost out there in front of the radical. You can evaluate this between 0 and 2 and 0 and 1. And looks like the order of integration doesn't matter in this case because you happen to be on a what? On a rectangle, correct? Because that's why the limits are constant. So at the end of the day, you get 13 square root of 2 over 3 for the answer for this surface integral. Do you see it? Sometimes we have multiple surfaces, okay? Then they want us to evaluate the surface integral. So this function is fxyz is equal to x squared plus y squared plus z squared. And as I said, ds is your area element, correct? Now, S is part of the cylinder, x squared plus y squared equals 9, between the planes z is equal to 0 and 2. So in other words, this PVC has lead at the bottom and at top, and it's closed at the bottom. This is the equation of the bottom. This is the equation of the top. In other words, the height of the cylinder is 2 units of length, together with its top and bottom. So in other words, here, this is a typical example of when you evaluating a surface integral over multiple surfaces. Notice here you have three surfaces, S1 the bottom, S2 the sides, okay, and S3 the top. So what we have to do is parameterize each of these surfaces one at a time and evaluate this surface integral for each of these surfaces and add up the results. Yes, it takes time, but it is what it is, right? However, we'll have a little bit easier way to do these in upcoming sections, but right now we're stuck with this method. So to parameterize the bottom of the cylinder is what? The bottom is r cosine theta, r sine theta, that is your x, that's your y, but z is 0 because you are at the bottom. Notice my parameters are r and theta. For sides, I took what? 3 cosine theta because you are on the sides, so the radius is fixed. So 3 cosine theta, 3 sine theta, and z is not fixed. It goes somewhere between what? 0 and 2. So my parameters for the sides of the cylinder is what? Are theta and z. For the top, I have what? R cosine of theta, r sine of theta, but z is fixed. You're at the top, so z is 2. So now, for each of these guys, I have to find the magnitude of the cross product of their corresponding what? Parameters. Like here, I have to find the magnitude of the what? Cross product of partial derivative of r with respect to r with respect to theta. Here, partial derivative of r with respect to theta cross r with respect to z. Here, partial derivative of r with respect to r cross product with partial derivative of r with respect to theta. So I got to find all this. And turns out when you do, you get R3 and R4 magnitude of those cross products. However, just to give you an idea how I got those R3 and R, here they are. So for first surface, do you see it? I have S1, so I took the partials with respect to R, with respect to theta. I took the cross product. This is what I got. And then I took, so this is the cross product, okay, of what? Of partial of R with respect to R with partial of R with respect to theta. But I have to take its magnitude, which is the square root of 0 plus R squared, which is R. On the other hand, for S2, I believe that was the sides, I have what? Partial derivative of r with respect to theta, partial derivative of r with respect to z, took the cross product, and at the end of the day, I got this. But now I have to take the magnitude, and when I do, I get 3. For the top, I have partial derivative of r with respect to r, partial derivative of r with respect to theta. Take the cross product, you get this. Take the magnitude, you get r. So now, what we have to do is go back to the function right here and replace, the kind of like express this function in terms of parametric equation of each surfaces one at a time. For instance, for surface number 1, that is the bottom surface, remember x's were what? Cosine of theta, y was r sine theta, but z was 0. So this is where I'm getting that. So this is like the function, what? Expressed in terms of what? Oh, what was it? R and theta for S1. Okay? This guy is the magnitude, which we found from previous page. And the area element depends on the what? Parameters. So in this case, my parameters were r and theta. So this has to be dr d theta. So this it's not polar coordinates. Be careful. Dr d theta came from the fact that my what? Parameters were r and theta. And lo and behold, when I evaluate this, I get this guy. Remember, this is not polar coordinates. What about this guy? Well, for this one, I have to use these parameters. Remember, this is your x, this is your y, and z is z. So when you do that, you will end up with what? Oh, what is it? 9 cosine squared plus 9 sine squared, which is 9. And then plus z squared, but z was z, so I still get z squared. And the 3 is the magnitude of partial derivative of r with respect to theta, partial derivative of r with respect to z. Then again, this guy is a function of the parameters, what was it? Theta and z. Guess what? Your area element is going to be dz d theta because your parameters were theta and z. Do you see it? Same thing for this guy, except now this is going to be function of what was the, I think the top was function of what? R and theta. Is that right? R and theta. So therefore, dA has to be dr d theta, not to be mistaken with polar coordinates. I know it kind of looks like it, but it's purely depends on these. Notice this guy was function of theta z, so the area element, dA was dz d theta. Okay, so you get an answer there, you get an answer here, so you add these guys up because you got to split it because you have what? Multiple surfaces, so each surface, each line, surface integral gets to be evaluated on its own respective surfaces. So you add up the results, and then lo and behold, you get 241 pi. So that's pretty much how we do these kind of problems. Now, a very quick example of this, that would be like finding the mass of a thin funnel in the shape of the cone. Z is equal to square root of x squared plus y squared. I believe this would be the upper half of the cone. Z goes from 1 to 4. If the density function, which is denoted by delta, is 10 minus z, sometimes they use rho for density, sometimes they use delta. So we are asked to find the mass of this thin funnel. So mass is equal to surface integral of what? Density times area. So this is the density, correct? And this is the area element. ds is area element, correct? So because the function was what? Expressed explicitly in terms of x and y, so I use that magic formula, which is the square root of 1 plus what? fx squared plus fy squared times dA. As a matter of fact, there is no magic about it. It's just like when you express the function in terms of, let's say, x and y. Let's say that's x, let's say that's y, and let's say this guy is fxy. So if you take the partial derivative with respect to x, you get 1, 0 fx. You get the partial derivative of what? This function with respect to y, you get 0, 1 fy. When you what? Take the magnitude of what? Rx with Ry, believe it or not, you get 1 plus fx squared plus what? Fy squared. So there's really not any magic about this. It comes from the what? The magnitude of the cross product of Rx, Ry, provided you have what? Parameterized the surface in terms of x, y, and fxy, which is your z, if z was to begin with was a function of x and y, correct? So there goes the density, 10 minus c, there goes that magnitude of the cross product, and because your what? Your parameters in this case is what? This is like a function of what? X and y. So dA has to be dy dx. And when you do this, so eventually you're going to end up with, when you simplify this guy, you're going to end up with this kind of fraction under the radical. These guys cancel, so you just get square root of 2. Okay, but now this is your z. Okay, because remember the density was 10 minus c, and this is the cross magnitude of the cross product. And now you can change this to polar coordinates. Because why? If you replace the z with 1 and 4, you're going to get something what we call annulus, which is like two concentric circles, same center, but different radii. So change this to polar coordinates. So dy dx changes into r dr d theta. And this guy right here is the square root of r, correct? Which r squared, which changes into r. And then r goes, as you can tell, from what? 1 to 4, and theta goes 0 to 2 pi, and lo and behold, you have the final answer. And in the next video, we will see the line integral over vector field. Thank you.